All right, let's start now looking at life annuities. So if you familiar with the insurance benefit, if you are good at insurance benefit, you did the problem sets that I posted for the insurance benefit. This should be easy. If you understood them, this should be easy. And I would say if you're not comfortable with those or you didn't do the problem set, you better go back and study the insurance benefit before you start the annuity. And this is for a good reason, because it will be an extension of the discussion we had in insurance benefits. So if you understand them, then it will be much easier for you to go through this chapter smoothly. So in this case now we will try to look at the life annuity, and we'll start with the continuous case. So it pays continuously. It's not at the end of the year or beginning of the year, but rather the payment is continuously, and whole life it stays until time of death. Annuity, the idea is it pays here. It's in insurance. When we talked about insurance benefit, the payment is made at time of death. This one, payments will be paid continuously of $1 a year, paid continuously, and it continues until time of death, right? So this is the opposite of the insurance, that this one, it ends by time of death. The insurance benefit, it makes the payment at the time of death. So let's go back to interest theory. Remember, in interest theory we looked at annuity certain, and when we say certain, it will give you the money certainly. So regardless of death or life. So the annuity certain, it's a series of payment. And let's say, look at the continuous one. Continuous one, if you remember, we called it the present value of annuity certain. We give it this one. Let's say for time of t, and it's equal 1 minus e minus delta t divided by delta, or it can be written 1 minus vt divided by delta. And this one, it gives you a $1 payment for a period of t. So every year you will get $1 payment, but the $1 is paid continuously because the bar tells us continuously. How we move from here to life annuity? Remember, life annuity is when we introduce actuarial, making the payment contingent on something, then we take the actuarial present value. It's not the present value, it's the actuarial present value. Right? I want you to see this, and there is no here. This is the actuarial. And the actuarial present value, because now we need to include the contingency or the probability. Then we take the expected value of AT. And what is T? Is the remaining lifetime, right? Remaining lifetime, which is a random variable. So if we take the expected value of this one, so we need to take expected value. Well, I mean, you can write it right away. This is continuous case from 0 to infinity. AT and FT dt. And this one also can be written 0 to infinity AT, now T px mu x plus t and dt. This is the general form here. This is the general form for this for the actuarial present value, and we need to give it another notation. Actually, for this actuarial present value, it's written this way. Now I want you to see what we need. For the insurance benefit, we use capital A. Now we're going to use small a. It's continuous case because it pays $1 continuously every year, and it starts at age X. Right. So you can write, this is the general formula. You might actually do it also in another way. Let's expand this little bit, because there is another way for this one is also, you can write it 0 to infinity, and instead of writing this one, all you need to write NEX. Actually, we need to use TEX dt, which this can be also written 0 to infinity. TDX is again, remember what's this actuarial discounting is VT multiplied by TPX. There is no mu because this is there is no, not like mu plus dt plus t dt. But just wanted to warn you, this one works only for expected value, or does not work for second moment. So if you want to calculate the variance or the second moment, you cannot use this one. It does not work for this one. You need to use either one of these or other form. So you need to square the a bar to 2, right? Second moment. We'll come back to this, but many times it's easy to deal with this one for the expected value, many questions. So you need to know all those formulas, but it's important, as you know, that we know the exponential distribution, and the other distribution that is very famous is the uniform distribution. Let's take a few examples on those things, right? But before taking example, let's also simplify it one step further. Wanted to simplify it one step further. Let's take now any one of these guys. So let's take sorry, let me use this color. Let's take AX. Remember, and we said this is the expected value of, or let's start from this point. Let's start with the annuity certain T. And we said this one, if you go back here, is 1 minus Vt over lambda, delta. Now this can give us delta A T, right, can be equal 1 minus Vt, right? It's very straightforward, right? What now? Let's take the expected value of both sides. Take the expectation, then delta is constant, it will go outside. Then this one will be expected of A delta T. The expected value of 1 is 1, minus stays minus, expected value of Vt. Now, this one is A of X by definition. Where I got the A bar of X is by definition. It says here, the actuarial notation for this is this, right? So we're using this by definition. But what about this one? And that's why I said if you know the insurance model, then this will be easy, the insurance benefit, because the expected value of Vt, is actually the AX, our friend. And because we deal with the continuous case. So now this one can be d delta AX equal 1 minus AX. So now we can rewrite AX is equal to 1 minus this over delta. And this is very, very important, right? Very important, this one, right? It's very, very important, right? Because many times you don't need to integrate, right? So this integration is just like in case you need them, but most of the times you really don't need to integrate. You right away, most of the questions you need to know this relationship. Let's take a few examples. As I mentioned, the famous distribution. Let's take our friend uniform distribution. So X is the remaining lifetime at birth. It's uniformly distributed, is uniform, is right, over 0. Let's make it between 0 and 100, right? So this is uniform distribution. So we need to find our friend maybe let's do A30. And what we mean by A30? The actuarial present value for life annuity issued to a 30 years old. What is the actuarial present value? So let's say somebody would receive $1 paid continuously from age 30 until life. How much the actuarial present value of this series of payment, right? So this one, you don't need to integrate. You can integrate, of course, but since you know this relationship is 1 minus AX, which is 30, we need delta. Let's say delta is given to be 5%. Let's give it. We need delta, right? Over delta. Straightforward application of this relationship. But what is A30? And now this is what I said. If you know the insurance benefit models, then this becomes very easy, because this is for uniform distribution is 1 over omega minus x, and then A omega minus x, which is 1 over 70 of A angle 70, the certain. We already calculated before in the insurance benefit, but if you use your calculator quickly, this will, this 1 over 70. Now this one E delta 5 multiplied by 70 divided by 0.5. This should give you my I need to calculate it quickly. Yeah, it's 0.2771. We calculated in the previous session. Now you take this guy here, then this one will become 1 minus 2771 divided by 0.5. So the value of the life annuity that pays $1 for this life is 1 minus 0.2771 divided by 0.5. It gives me 14.458. Right? So it's easier to use this formula, right? It's easier to use this formula. It's easier than doing the integration. You can still do the integration because this is easy distribution, the uniform distribution. Any of these functions can work for you. If you want to do, you can try it. But since it's easy distribution, we don't need to, or we know the formula, we can do it quickly. Now let's take the other important distribution that we have questions about. It is the exponential. Let's take a second example. Now x is exponential. And what is x? Remember, it's the remaining lifetime random variable for at birth. The remaining lifetime is exponential with, let's take the general form with mu and delta, and we need to find a general form for ax, right? We need to find the general form for exponential distribution, right? Remember, it's exponential, and exponential has constant mu. Mortality is constant, right? Or mortality rate. This one we apply the same rule, the same formula here. We need to apply the same formula here to this one, which is 1 minus E minus delta. Now, sorry. Let's do it from the beginning, because this is AX divided by delta. Right? So we following this rule. Now I want you to remember what is AX. Recall, for exponential distribution, only for exponential distribution, this one mu over mu plus delta, right? So now let's take this one up here, becomes 1 minus mu over mu plus delta. Everything is to delta. If you multiply across, it becomes mu plus delta minus mu divided by mu plus delta divided by another delta. Now let's cancel this one plus minus, they cancel out. Now this one cancel out with this one, we left with 1. So what is left for AX for exponential distribution is 1 over mu plus delta. And this is very useful for exponential distribution, right? Very useful, right? You should see questions like this in midterm, in final. Yeah, you should expect questions based on this relationship. And if you take actuarial exams, many questions they require you to know about this relationship. Like if you want to take example, now x is exponential with mu equal, let's say 10% mortality rate, and delta, let's keep it 0.5%. Now let's find AX, right? If you find AX, it's easy. It's 1 over mu plus delta, which is 1 over 10 plus 5.15. So this one will give us 6. It's easy, straightforward. There is nothing complicated about this kind of equation, right? So it's very, very easy. Right. Let's go back again. Let's go back. Remember now we have certain annuity, we said it's A T, which is 1 minus Vt divided by delta, right? This for the continuous case. Now, what we did, if we take the expected value of AT, we establish it to be AX, right? Which is 1 minus AX divided by delta. Now, what is the variance? And we need the variance many times to calculate, risk measurement. Like in insurance, you need first you issue what this is the expected value. On average, actuarially, the value of the series of payment that is contingent on life will be this amount. But many times for riskness, you need to take a measure of what is the variation you need. So the higher the variation, it's riskier. So it needs that you need to take to control the risk by increasing the amount you need to keep. But so we need the variance, right? We need the variance. As I warned you before, we cannot, use for second moment. We cannot, we cannot use this kind of integration, only the first one. But we can use also the relationship between the insurance model, the insurance benefit, and the annuity. So let's start with A, defining what is A. Again, what we did before. AT is 1 minus Vt divided by delta. Now let's rewrite it a little bit differently. 1 over delta minus, or let's keep it a plus so it helps us. Now 1 over delta minus Vt, right? So I wrote it this way. Now let's take the variance of this one. So the variance of 1 over delta, this is a constant, it's 0, plus the variance of 1 over delta Vt, we take the constant out, but we square it, and then variance of Vt. What's the variance of Vt? This is the insurance benefit, the variance of the insurance benefit. So the variance of A angle T is equal to, now this one here, recall, this one, if you go back to the earlier session, for this one, it will be TEX minus AX to 2, right? So then the variance of the annuity, life annuity, is now TAX bar minus AX, the expected value to 2, divided by delta raised to 2. And this is also very, very important, right? These formulas are very important. You should expect, you know, like you get questions like this in the exam, right? So this is very important for us. Let's take one example. We'll take a few examples actually, but let's take one example now, and then we take a couple of or a larger example. Let's take example 1. And we'll again, let's do the uniform. And now we need to find a variance, the variance of the life annuity. Or let's define it usually. That the question will say y is a whole life annuity issued to 30 years old. So and now we need to find variance of y. We need delta. Let's keep delta 5%. So what is the variance of y? Simple. If you know the form, you can always, you know, integrate, find the second moment, find the first moment, and then you do the typical variance. But if you know this relationship, you don't need to do that. We write it right away, 2ax. I usually write the formula and then see what I have and what is missing. So we need this, we need this, we need all of them. We have delta. But 2ax for uniform distribution, it's the same as expected value, but at 2 delta. So this will be, if you recall, if you go back to your notes from the previous session, this will be 1 over 70. A 70, but at 2 delta. So you do everything is the same, but at 2 delta. So this will be 1 over 70 multiplied by 1e minus 2 delta over 2 delta. Now this one you can get it if you do the calculation. We did it in last session, so I don't want to spend time redoing the same example. But this one, what you would get for this one to be 0.1427. Now you need AX, which we calculated it just a second ago. AX will be 0.2, I think 2771. We calculated in the previous example. So variance of y will be again 2ax second moment minus ax the first moment, but square. And here, like, you can replace all x by 30 because the age is 30, 30, 30, 30. Divided by delta raised to 2, which is 0.5 raised to 2. Right. So we take 14.27 minus 2771, and this is raised to 2 divided by 0.5 raised to 2. If you calculated it, it will be, I already calculated it, it's 26.366. We would see there is nothing new up to this point. Something we already calculated before. The only thing new in new formulas, and it is very mechanical, so you can quickly answer questions like this. But let me take another one, another example. You know, it can be variety of examples. Let's take another example. This question is a little bit twisted. So now, given what is given is delta force of interest is equal mu, and mu is constant. Both are constants, and both are constant. So we know we're dealing with exponential distribution. So what is the, we are given also that this one is equal 12.5. What the question wanted us to find? It's the question is find variance of ATX. You know what's variance of ATX? Like the variance of the like life annuity paid contingent on life. TX is the remaining lifetime random variable. So what's the variance? Simple. We need to apply the same rule. Let's start with what we know. The variance of ATX. Let's start with what we know. This is the general form and this continuous case. This is the general form. There is nothing new here. Now we're gonna take one by one. We need this, we need this, we need this. Let's take TAX. What's TAX? It's exponential distribution. Now it's the same thing but at 2 lambda. Remember if you go back in uniform and exponential distribution, remember this one, right? I said it's very important. So question like this, we know what is or we know that one because it's given here, so we can use it to find delta and lambda. But even with this one, we can find it you can find delta or mu. But this one you can find it also without delta or mu. How we can find it without delta and mu? Now this one, if you remember, it's it's mu from the previous chapter, mu plus now the same thing but 2 delta because it's the second moment. But delta is equal to mu, right? So let's keep, because we have a mu in the numerator, let's keep everything mu. Same logic. If you have AX will be mu over mu plus lambda, which will be mu over 2 mu and half. You don't need even to find delta up to this point. But now we need delta. We need delta. So we remember, like we can take this fact. AX is equal to 12.5. It's given, which is equal for exponential distribution. We know the general form that we found it in this session, which this over delta, which is like, let's make it 1 over 2 delta because they are equal, right? These again, these are equal. Given the question, they are equal in this case, right? Multiply across 2 times 25 becomes 1 over delta, or sorry, delta, or delta is a reciprocal of 125, so it's 4%. Right? Clear? So this is very easy. Now we got this, we got this, we got this. Now we go back to the formula here. We got everything we wanted, right? So this one will be 1/3 minus 1 to 2 divided by 0.0422. If you use your calculator, 1 divided by 3 minus 1/4, which is 1/4, which is 0.25, divided by 0.04 raised to 2, you will get 52.083. Okay. It's very simple, very simple, very simple. Now let's take another example, harder example, little bit harder. As I mentioned, you know, the insurance, in insurance calculation, we usually use the you know, the actuarial present value. Nobody charge it. This is just like, you know, on average, this is what you expect the value of the life annuity. But in practice, you need to have a measurement of risk because, you know, there is variation. So you need to capture this variation, this risk. So you need to have the fund bigger than a certain, bigger than, you know, like the average actuarially balanced value. And by how far? Usually you would have a riskness measure. Let's take one example here. It was one of the Actuarial Society of Actuaries exams. Let's look at it. I just took a photo of it, so from the website of the Society of Actuaries. So let's take a look at this example. This is a little bit harder. So the question here, we have a fund that is established to pay annuity. We have 100, and it's very important to read that independent life here. Age X. Each annuant will receive 10,000 per year continuously. That's another important information. So the benefit amount, so benefit amount is 10,000. Now we have number of individuals. We have 100, right? 100 lives. So we are given, calculate the amount in millions needed for the fund that the probability using the normal approximation is 90%. So we need the fund that 90% of payment will be here, only exceeded by 10% as riskness measure. Let's take it step by step. Let's take this question step by step. Now let's define what is Y. Or like for, let's start for one life. For one life, let's take one life for one, for an individual. So we have now for one individual, now expected value of Y. Let's say Y is the like the benefit, like the benefit amount, VT. Right. The expected value of Y, what every individual like actuarially balanced value will be, because we have 10,000 the benefit, and multiply by expected value of the whole life insurance, which is AX continuous, because it says it's continuous, right? It's very important. Now, what is AX? Well, this can be 10,000. Now, the relationship between AX and A capital X is 1 minus AX divided by delta. If you would replace what you have here is 0.4 and delta is 6%. This one will be now 6 per 10,000 for individual benefit, multiply by 0.4 divided by 1 minus 0.4, 6 divided by 6%. So we 6 by 6%, it will be 60, and this will be 600,000. Did I get it right or not? Maybe I should use a calculator instead of making a mistake, right? So this one will sorry, no, not 60, I mean 10 should be 0.4 divided by 0.06, 0.6 divided by 0.06. Now 10, I meant 10, it's 100,000. Okay. So this is the 100,000, right? So AX here, just to keep it in the side 10. But we need, this is, we got the for one individual. So for the whole fund, let's call fund is like individual 1 plus individual 2 up to like 200, or this will be Y1 plus Y2 plus. So the expected value of the fund that we need to have then on average will be 200 multiplied by the 100,000. right? Because we have 200 lives. Oh, actually 100 independent life. Sorry, it's not 200, it's 100 independent life. So this will be 10 million, right? It seems I made a mistake. Sorry, I made a mistake here. Just can I calculate one more time? So the benefit amount is just 10,000. Let me just do it again. Seems I did a mistake. 1 AX is given 0.4. $100,000 multiply by 100. So yeah, 10 million, right? We need 10 million. Now this is the first one. Now we need the variance because we need 90%. We need the variance. We do the same logic. We do the same logic we did for the expected value of the fund. We start with an individual. Let's start with one individual. For we need first like variance of ATX, and this can be TAX from the definition minus AX to 2 divided by delta square. So now ATX is given to us by the question. It's 0.25. 0.25 minus 0.4 squared divided by 0. Let's double check, just 6%. Let's do this one. You would get for one individual is 25. Not for one individual, for 80, but for one individual. Now variance of Y, one individual, will become the variance of the benefit amount, which is the benefit amount is 10,000. And a T. And if you take the 10,000 outside, it will become 10,000 raised to square it, and variance of 80 multiplied by 25. So 10,000 raised to 2 multiplied by 25. And then whatever the number, I'll keep it in the calculator. Then for the fund, now F is equal to individual 1 2 all the way to 100. So now if you take the variance of the fund, they are independent lives. Because they are independent lives, so we have 100 lives multiplied by variance of Y. So this will, now let's multiply it by 100 again. So we'll have 2.5, 10 raised to 11. Now what is the standard deviation of the fund will become, we take the square root of it, will be 500,000. The square root of the fund, right? The standard deviation. Remember, we need the fund to be able to cover 90%, and this 10%. So now we need what is Z here, because we need the amount here to be expected value of the fund, and you add to it Z9 multiplied by sigma of the fund. We already calculated the expected value of the fund. And the expected value of the fund, we said it's 10 million. Z, like the exceeded, you know, from normal distribution, go to the normal distribution table and you get Z, the 90th percentile, or exceeded by only 10%. This will be 1.282, right? And then this one, you need now to multiply it by the standard deviation, which is 500,000. Okay. And if you do that now, multiply by 1.282 plus 10 million, you will get 10,641,000. So the fund needs to, in order for you to pay for this 100 independent lives, you need to keep in the fund 10,641,000 to be able to pay with 90% accuracy, right? But if you want to do it not without any insurance, without like the expected value, without any risk management, then the actuarial balance value will be simply 10 million. But because of the risk measurement, you need to keep extra money to be able to be certain. This one will be on average 10 million you need. And this one for risk management, you need to have not 10 million, but you need to add extra 641,000. With this, we finish this session. We'll come back to other sessions as we move on life annuity.